In this problem, we have a bar being subjected to an axial force that is resulting then in an axial displacement. When the time begins, we're going to release this force and release the bar, and we want to see how the bar is going to respond to these initial conditions and then vibrate in the axial direction. We want to find the response of the bar, which we are going to call u of x and t, will be that horizontal displacement from each point's equilibrium point at all points in space and all points in time. So we're going to need to start with the model of this system. So for this continuous system, really what we're going to try to do is identify the things we know, the things that are constant, which are going to be important here. So we are told it has a constant cross-section, A. It is of uniform density, so rho. It's of uniform material, so the Young's modulus E is also going to be constant. And we know that when we let go at time equals 0, there's not going to be an applied force anymore, so it's going to be free vibrating, which we can see in the identify step. So since these things are going to be constant, that is going to allow us to use the differential equation, or the equation of motion, that c squared del squared u del x squared equals del u squared dt squared. So this is allowed because we have this free vibration, so there's no forcing acting on it, and A, E, and rho were constant, and they're going to be, rho and E are going to be absorbed into that C, where we know that C is going to be the square root of our Young's modulus over the volumetric density rho, both of which are going to be provided here. And then the A's are able to cancel out because A is constant. So in our identify step, and this is really kind of the model and the equation of motion in one for this system. So looking at the differential equation, the partial differential equation that we came up with, again, it's going to be free vibrations. And we have the constant A and rho and E, which actually were necessary to get that partial differential equation, but they'll be important for coming up with our solution for u of xt. We know that u is going to be separable. That's the strategy we're going to use to solve this. So it's going to be a u that's a function only of x times a t that's a function only of time. And what that's going to look like when we put it all together is it's going to be the summation from n equals 1 to infinity of our eigenfunction that we're going to find, u sub n, times, and we're going to have a cn term times a cosine of omega n t, plus a dn coefficient times the sine of omega n t when we find those natural frequencies. And that's the form our solution is going to take. So we need to find our eigenfunction, capital U, we need to find our natural frequencies, and then we're going to need to find these coefficients in order to come up with our closed form solution, this infinite summation of terms. And finally, important to identify here is it's going to be a, well, I'll call it a bar, or we could call it a column. It's important to realize we have a beam or something that is in pure axial deformation. We're not going to have any transverse loading happening. We have no moments happening. If we did, then it goes into another kind of problem that we're going to address in a following section. So based on what our closed form solution looks like, we can start to come up with some of these parameters we're going to need, starting with the eigenfunction and the natural frequencies here. So let's start with what is the form that u of x should have. So this is coming from the fact that it was a separable equation, and we know that the assumed form, or the kind of generic form of u of x, is going to be a times the cosine of omega over c times x plus b sine omega over c times x. And what we're going to want to do is we're going to, because we have homogeneous boundary conditions, as we're going to see, one of these coefficients is going to drop out, and we're going to be able to get from here the natural frequency. The natural frequencies will then give rise to the eigenfunctions. So let's address what are the boundary conditions for this problem first. So in these axial type of problems, the boundary conditions will be locations where we know where the displacement is, the value of the displacement at all times, or where we know the axial strain at all times. And we'll have two of them because it is a second order ordinary differential equation in U. So going up to the problem here, we have a wall at x equals 0, and we have a free end at x equals L. So what that is going to tell us is that our first boundary condition is going to be that U of 0 is 0. The displacement at the wall is 0. The point directly connected to the wall cannot deform. It cannot move left or right because it's attached to the wall. And then the second boundary condition, which we'll get to then, will be actually on the axial strain. So that is going to be du dx, which we can also write, and that's evaluated at L, the free end, is more succinctly u prime of L is 0. There is no axial strain on the free end. It will have deformation, but will not have strain. So let's start with the first boundary condition and enforce that by evaluating u at 0. So we're going to get a times the cosine of 0, and that's just going to be 1, plus b times the sine of 0. Well, that's just going to be 0. So this tells us that a is 0. Similar to the string problem, that a coefficient is going to be 0, so I can get rid of it from my u equation to make this a little bit simpler. Right, so a is 0. Now we can go to the second boundary condition on the strain at L, the axial strain at L. So I first need to find, I'll find u prime of x first, which now that I already know for this one at least that a is 0, I will not differentiate that first part, that just goes to 0. And then the second part I am going to have here omega over c when I use the chain rule on the b sine of omega over cx. And the sine will go to a cosine, the b comes along as well, omega c times x. All right, so now let's evaluate u prime of x where x equals L. So I have this omega over c times b times the cosine of omega over c times L. And that has to be 0 because the strain at the free end is 0. So to avoid the trivial solution, like we saw with the string problem before, mathematically we could say that b is also equal to 0, but then u of x is identically 0, and then we have no oscillations. So again, that can't be the answer to this because we are giving it an initial deformation, so it must have a non-zero deformation, non-zero oscillations in this system. So we are going to enforce that b, since a is 0, b cannot be 0. So what that lets us do is we can divide through both sides by omega over c, because omega and c are both non-zero. B we know has to be non-zero, so then 0 must equal the cosine of omega over c times L. So if the b part is not 0, what makes this term 0 must be the stuff inside the cosine. So it must be this omega that is making this term equal to 0. So now we have this cosine on the right-hand side. We want to free this omega. So I want to take the arccosine, or the inverse cosine, of both sides. So the right side is easy because that is just omega over c times L. And now I want the inverse cosine of 0. So when I take the cosine of what, does it become 0? Well, the first time it's going to be pi over 2, but also 3 pi over 2 and 5 pi over 2. In fact, every odd multiple of pi over 2 is going to result in 0 when I take its cosine. So there's not a unique solution to taking the arccosine of 0, and that's what's going to give us the infinite, as we'll see in a minute, the infinite natural frequencies and then infinite eigenfunctions for this. So again, odd multiples of pi over 2 all satisfy this. So what we can say here is, to make it odd, I'm going to say that 2n minus 1 times pi over 2, where, just like before, n is going to be an integer. And it's going to go from 1, 2, 3, 4, 5, etc. Right, so this is going to guarantee that the left-hand side is always an odd multiple of pi over 2. For example, when n is 1, which is where we're going to start, then we're going to just have pi over 2. when n is 2, we're going to have 4 minus 1 is 3. 3 times pi over 2, again an odd multiple of pi over 2. So I want to rearrange this. I want to solve for, now I'll call it this omega sub n, and that's going to equal this 2n minus 1, and I have to multiply by c, so pi c over L. And then I have the 2 carrying along as well. Right, so my natural frequencies for these boundary conditions, 2n minus 1 times pi c over 2L. So notice they are different than in the string example, where there we knew that even though it was a string rather than a bar, the boundary conditions would look the same. When we got to this second boundary condition in the previous problem, we had a sine of omega c over L left, and then we were left with pi, 2 pi, 3 pi, etc. But here we have odd multiples of pi over 2, so the natural frequencies look different. So now we can put this together and form our eigenfunction. So our un of x, what do we have left over? The b, which I'll write down, but I'll get rid of it because we know that will be absorbed into the cn and dn in the next step. But I'll write it temporarily, times, and from the original function, sine of the omega over c, so that is going to leave us with 2n minus 1 times pi. The c's are going to cancel over 2l times x. Again, I'm going to get rid of the b and let it get absorbed into the next coefficients when I write this. I could also more succinctly write this as the sine of omega n over c times x. I write again as above here in that original formation of this. So those are the eigenfunctions and the natural frequencies for this particular system with these boundary conditions. Again, we want to keep in mind that our eigenfunctions or mode shapes and natural frequencies are going to be dependent on the boundary conditions in continuous systems. So even with everything else being the same, if we look back to the top here, if instead of a free end at the right side, it was another wall that was connected to, our boundary conditions would be different, because then we would know the deformation at L was 0, rather than here where we know that the strain at L is equal to 0. All right, so that is found. Now we can move on and start looking at the solution for the time pieces, the initial conditions. So again, what we're looking at here, now that we have our eigenfunction, we want to, let's scroll back up to where we're looking at in this identify step. We have our un of x, we have our omega n. Now we're interested in the cn and the dn values for this, which are going to take into account our initial conditions. So let's set this up. We remember from the slides that cn is going to be found by taking 2 over L times the integral from 0 to L, I'll use little l in this case, of our eigenfunction times our u0 of x0, our initial condition, and we want to integrate that with respect to x. And then the dn is going to be looking very similar, where we'll have 2 over, now we'll have an omega n out in front, L, integral 0 to L, our eigenfunction, times our u dot of x comma 0 dx, so our initial velocities. So we need to identify the initial position everywhere and the initial velocities everywhere for this one. So actually the velocity in this case is again easy. We're going to be holding this bar out with some applied force, and then it's starting from rest when we let it go. So it has no initial velocity. So that means that the velocity everywhere, u dot of x0, very easy, simply 0. But we also need to identify the initial position, or really the initial deflection of the beam from its equilibrium point. So in the top picture here, it's in equilibrium, it's at equilibrium length of L, and then we're stretching it out. Every point along the beam is being pulled to the right of its equilibrium position. So every value is going to have a value of u for every x position, except at the wall where it's firmly, rigidly attached and it can't move there. Now in a beam, the amount of deformation is going to depend on how far away we are from that cantilever side. The end where L is going to deform more than when we get closer to the wall until we're all the way at the wall and it's 0. So if we remember all the way back to strength and materials, we can figure out how much deflection we have or how much deformation we have with that. At the end of the bar, we'd use like PL over EA. We're going to use the same idea here, that U of x0 initially is going to be P, which in this case is F0, is our applied force, times, or divide by EA, and that's going to be a function of x in this case. So when x is equal to little l, that is the end of the beam. That's how far that point is going to deform from its initial condition. But when x is 0, when we're at the wall, then we're going to find that u is 0. There's no deflection, and that should be the case. And then anywhere in between, it's going to be this linearly increasing amount of deflection as we get further and further from the wall. So we don't want to say it's uniformly PL over EA, because not every point is going to deflect the same initially. It's this PX over EA, so that it is going to linearly vary. So we can look at dn first, actually, and do that really quickly, because we know that u dot is 0 everywhere in this one. So that means that dn, like in the previous example, is going to be 0. That term will just drop out. And then we have our Cn term that we need to determine by taking that eigenfunction and then multiplying it by this u of x0, which we just defined above. And for this, we can use Mathematica to do the integration for us. Since it will have to use integration by parts, we can skip a step and let Mathematica do the calculus for us. So in the Mathematica, I'm going to define my eigenfunction of x is going to be this sine, and I'll put the long form here is this 2n minus 1 times, and I'll get the fraction, pi over 2l times x. All right, so eigenfunction has now been defined properly, and now I can define my u0. I can also do that as a function of x, is this f0, and I'll do this with the fraction, over ea, I'll call it ey because you see it thinks that I'm talking about the 2.1828 number, so I'll call it ey here, times x. And that also is now defined properly. Right, so my Cn, I'll call it Cc for here, of n, is going to be 2 over L times integral from 0 to L of my u of x times my u naught of x times dx. Okay, so it did that for us, but we see that we have some terms that are going to be able to be simplified here. So let's say full simplify of, right now I'll just take the above, and I can again tell it that n is a member of integers. So it's going to simplify it down for us. In this case, we don't have to tell it that the L is positive or anything like that, so that makes our lives a little bit easier. So it's this expression now, so it knows n is an integer, 1, 2, 3, etc. So now it's able to simplify this sine term and this cosine term, and we get this more compact term that we're going to be able to use for our C sub n. So I pasted it out of Mathematica. I'll just recopy it here a little bit nicer. Right, over our EA 1 minus 2n squared pi squared, and then it's this alternating series -1 to the n. So we are finally ready to assemble our solution now. Going back from what we saw in the identify step, We knew the form it should take. We have our eigenfunction. We have our natural frequency. We now have our dn. We have our cn. So let's put it all together. So assembling u of xt is the infinite sum from 1 to infinity of our eigenfunction, going back to its definition here, this sign, and I'll put everything in kind of the long form, writing out what the natural frequency is, 2n minus 1, and we have a pi over 2l, since the c's canceled each other out, times x. Right, so again, that is the eigenfunction. Now we have our Cn coefficient, so a negative 8 f naught L over Ea, 1 minus 2n quantity squared pi squared, and it's that alternating series, times, and what do we have left over? That Cn, remember, is being multiplied by the cosine omega nt. So I have to include that too. Cosine of 2n minus 1 pi c over 2l times t. And that's in parentheses. All right, so that is that full solution. And I can write it a little bit more compact. I can take some things out here. I'll make it a little bit less. So the negative and the 8 can come out. F naught is a constant. The L is a constant. Those all can come out. The E and the A and the pi squared, those are going to be constants, so those all get dragged outside of this summation. And out in front, I'll have this negative 1 quantity to the nth power over this 1 minus 2n quantity squared. And then I'll have my sign of, I'll write it more compact here, omega n over c times x times the cosine of omega n times t. And that becomes the complete solution for u of xt. It tells us the horizontal displacement of every point on the bar at all points in time as this infinite sum. And again, if we take a look at what's going to be happening here, we have this 1 minus 2n quantity squared in the denominator in that summation. So what's going to happen is n gets larger as the frequency gets larger. These terms are going to get smaller and smaller and smaller that we're adding, and it's going to converge to our solution. Analytically, this is the solution. Let's go and numerically see what does this look like when we plot it over time and over space. What is happening to the bar as it oscillates? So in MATLAB, we can make some of these calculations. I'll put in those properties that we were given about the modulus of elasticity, or the Young's modulus, that volumetric density. We can calculate C, which we can see here is about 5,050. We have our initial static force, our length, so everything is put in here, and I am going to simulate this initially over 5 milliseconds, because we're going to see that these oscillations are very fast. So if we plot it for too long, it's just going to keep oscillating over and over and over again. So we'll just zoom into a smaller amount of time, 5 milliseconds. So first I am going to define my natural frequencies, just as we did when we were doing this by hand, when we were doing it manually. So that 2n minus 1 pi c over 2l are the natural frequencies. And we're going to see what they turn out to be, because we're going to use them for comparison when we look at finite element analysis in the next section. So what I'm going to look at here is assembling my solution here. So on line 73, that's why I have inside the summation when I was doing this by hand. And what I'm going to do is going to keep adding that to my solution. I'm going to here, for this example, take 15 terms. So this will only include the first 15 natural frequencies. But as we saw, by the nature of this 1 minus 2n quantity squared, the addition as we get to larger and larger n's becomes smaller and smaller and smaller, and it's going to have much less of an effect. So this is going to give me my u, my deflection for all of my points. I'm going to take initially 20 points here over all of my time steps, which I'm taking these very small time steps here. so about 10 microseconds. Right, and then I'm going to animate that, and we'll see what that looks like. So let me just run up to that point. All right, so what we have happening here, larger, is x is going to be every point's initial position when it's in equilibrium, and then the red square is where it is over time, right? Because u is defined from the equilibrium position at every point. So what I'm finding is how much it has changed from its equilibrium position. So what we see, I'll run it again, is that it just keeps oscillating. All the points are going to the left, all the points are going to the right, so it's getting longer and shorter and longer and shorter. And we did not allow for any of our dissipation here. There's no energy lost, so it does just keep getting longer and shorter as time goes on. It's not going to eventually relax back to its equilibrium position. And we see that it has more value of u as we go to the right on that free end, whereas the left end is barely moving at all. So looking at it just one more time. So we see at the wall, the square doesn't move at all because there is no deflection, and then it moves only a little as we go from that wall as we go to the right, and then there is more and more displacement as we go to that free end of the bar. Now, I did exaggerate the amount of motion here, as we'll see in a second. The points are not actually moving that much, but if we put it into the correct scale, we would not really notice it moving at all. So let's see, what is the scaling I used here just to exaggerate it so we could actually visualize what are all the points in the bar doing. So going down to here, what I'm actually plotting here is I'm actually multiplying it by 10,000. So this is exaggerated 10,000 times so that we could see visually what the bar is doing. And let's also see what are, let's just look at the first two natural frequencies since we'll be using these later. So I have that definition of Wn. So I'm going to be able to find the first natural frequency when n is 1, the second natural frequency when n is 2, etc. Let's just see what the first two are. I'm going to show these in hertz. Right, so we see here about 1262 hertz is the first natural frequency, and then the second natural frequency here, 3786 for the second. And we could go further, but the first two are going to be the ones we're going to concentrate on, and we'll compare these when we look at this problem again with finite element analysis. All right, so now I want to track just what are some specific points doing. I want to look at what the points at the end, halfway through, and a quarter of the way through the bar, how much deflection are they experiencing? So I'm going to plot that against time now, not as an animation, because I'm only trying to track these 3 points to see what's happening. All right, and if we see what is going on, my y-axis, that's in micrometers of deflection. So that is moving positive to the right of the equilibrium point and negative to the left of that equilibrium point. As we should expect, the deformation at L is larger than the deformation at L over 2. The red line is larger than the deformation of L over 4. As we get closer to the wall, we are experiencing less deformation. If we see the pattern and the shape it makes, it looks like this, at least for at the free end. It looks like more or less this triangular wave happening here, where it goes to its maximum, right back down to the minimum, right back up to the maximum. Whereas for all the points closer to the wall, like at the halfway point, the quarter point, it's going to go down, and then it has this dwell at a maximum. It goes down to its minimum, it dwells, it goes up, it dwells. So they're all having this dwell, but they go along that same line as time is going on. So again, I'm only tracking here 3 points for illustration, and we'll see when we do this again with the FEA, when we compare what's going on with the here exact solution. What are we getting when we apply finite element analysis? Are we getting agreement or not? And finally, I want to look at the frequency spectrum. And I'm going to look at, again, just 1 point of view, and I want to see in the frequency domain, what is it doing? So for this one, I'm using a little bit better version of a power spectral density function than when we do it by the long way, kind of using fast Fourier transform. I'm going to use pwelch to do this. That's going to use windowing. It's going to give us a little bit better result than the way we typically have been doing it with taking the FFT and then looking at those coefficients. So we get a little bit cleaner of a signal. So this is what we are getting for the power spectral density. This is in here in Hertz. So we're seeing these strong frequencies happening at the natural frequencies. So let's just see what we get here. And the quality of this is going to be dependent on how long we sample, and it's going to be dependent too on how fast we sample. Well, that's going to be the x-axis that depends on how fast we're sampling. So we probably could sample longer and get some better results here, but we see we have a peak at about 1172, and if we compare that, and this is in Hertz, so if we compare that to that first natural frequency, it is close. We probably don't have enough quality here. Let me increase how long we're sampling for so that this comes out maybe a little bit better. And I'll rerun this so I have more data that I am working with. And I'll rerun this pwelch now. All right, now we have much stronger peaks because I ran the simulation for longer, so the resolution is becoming much, much better. So we see clear peaks we have in our signal now. So now if we see where the first peak is, 1270, that is matching much more closely now to what we get analytically, that 1262 about. And if we ran this even longer, we would see the same thing. All right, so the peaks on these, I'll check the second peak as well. I have this 3809 Hertz coming out of the pwelch. Again, matches pretty closely to what we get from the analytic solution from the 3786. And again, sampling it longer, I would probably get even closer to that value as my resolution is going to increase. So we see a bunch of peaks here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 peaks, and then the peaks stop here. So we would want to know, why did the peaks suddenly stop after 15 of them if we're going to have an infinite number of natural frequencies in continuous systems? Well, keep in mind, what am I taking the pwelch of? I'm taking the pwelch, or I'm making the power spectral density of the data that I got through simulation, that I got through this for loop up here that was calculating my W of xt for all points in time and all points in space. But it is doing it numerically. I had to truncate that infinite sum that is exactly how the system is behaving, or analytically how it's behaving. But remember, I decided to only do this for 15 frequencies. I went to the wrong one. I decided to only do it for 15 frequencies. So that's why we see that drop off after 15 of them, that there's no more peaks. Well, it's an artifact of simulating our data and truncating it at only taking 15 of the terms. If I increase this, then we're going to see that, yes, we do keep seeing those peaks going, and there should be an infinite amount of them, or an infinite number of them, but we have to cut it off at some point so that we can run this simulation. So there should be peaks keep going for all of the infinite natural frequencies here if we ran this with even more detail.